Hi, everyone, and welcome to this episode of Crowded Beaker Solves. Today, we are continuing a series on chemical kinetics. And if you watched our first video, in that video, we talked about rates of reactions and how we can quantify the rate of reaction, typically in units of like moles per liter per second, or atmospheres per second, or some similar thing where there's a quantity, a concentration, an amount versus a unit of time as the rate that we report. And now in this episode, we're going to get into something called rate laws. And rate laws, you'll you'll see a lot, are equations that generalize a chemical reaction. They sort of describe the way the reaction works, and it governs how the reaction happens down the line. So each reaction can be generalized by a rate law, where the rate that we found in, say, video number one is going to be equal to a constant, which is unique to every reaction under every set of conditions, and times the concentration of reactant A and the concentration of reactant B, which are then raised to certain exponents, which we are called orders. We're calling them orders. X and Y have to be experimentally determined. We're just going to lead with that. Sometimes it's tempting if in a balanced chemical equation there's like a 2 in front of it, a coefficient of 2, to be tempted to say that that's a 2, but it's not. There's often no correlation at all. So X and Y are experimentally determined. Let's look at a couple of very, very general examples to see how that would affect anything. And we're just going to use A as some generic reactant in our equation. So if the rate law was written as rate equals the constant times A, and there's an exponent of 1 here, that would mean that A to the 1 is just A. And that means because this is a constant, the rate of reaction is actually proportional to the concentration of A at any given time. So whatever A is, its concentration will determine the rate proportionally. Okay, so that would be a first order reaction. That's how we say it, first order. But what if the exponent was a 2, in which case it would be second order? Let's think how that would affect anything. In this case, the rate is proportional to the square of how much A or reactant is present. So whereas in part 1, if I double the concentration of A, I would double the rate because it's set against a constant. But if I double the concentration of A in this one, the rate would go up by a factor of 4 because now we're squaring the doubling. So double squared is a factor of 4. And that's a second order reaction. What if, though, the exponent there was a 0? What if it was 0 order? Well, if you know from math class that anything raised to the 0 is just a 1, this basically becomes a 1, and the rate is now a constant. There are some reactions that proceed at a constant rate, regardless of how much stuff is there and what you do with it. And so that would be a 0 order reaction. There are other orders of reaction, but in AP Chem, which is what I teach, we are only required to know the first, second, and 0 order, or some combination of them. We're not going to get into fractional orders, at least at this point, which they exist and they're kind of ugly. But what if you had two reactants and both of them can be expressed by an order, like A is to the first order, but B is second order? We would say it's first order in A, second order in B. Maybe this reaction is the rate is proportional to A, but proportional to the square of B. That happens a lot. And we would say it's third order overall because we have the magnitude of 3 exponents present there. Now, in our first video, we looked at the reaction of decomposition of N2O5, and we saw a couple of graphs there. That actually is a first order reaction. So the rate slows down as some of this got used up, and it's proportional to how much is there at any given time. Okay. And you might now be wondering, how do we know what those numbers are? You said it's supposed to be experimentally determined. So how do we do that? I want to do a couple examples with you to introduce that. I will probably do a second video on these as well as they get a little bit more detailed. So what we have to do to determine the rate law for a reaction is we have to run experiments. We have to run some trials, usually more than one, and do things like change the concentrations of the reactants and see how the system responds. So, for example, if there was a reaction between this molecule and some OH ions. At this point, I'm just going to ignore what the products might be. But let's say that those are reacting. And let's say my initial concentration is 0.05 and 0.05 in experiment number 1. And that I find that the rate of reaction, the initial rate, this is called the method of initial rates, is 0.00034 moles per liter per second. Okay, great. That's good information. What if I run the trial again, keeping one of them constant, but let's say double the concentration of the other one? Let's change the concentration over here and see how the rate responds. So in this case, I doubled the rate, the concentration here, and the rate also doubled. And that tells me the rate is proportional to the concentration of this. It's just an equal proportion. And so I can say that that is first order with respect to OH. There's a little 1 there. We can actually write it if we want to. Okay. Let's pull this up just a tiny bit. And then what if I do a third trial in which I keep the OH constant now that I know it, and then change or double, in this case, the initial molecule, and I find again that the rate doubles in response to that. So that means that it's first order with respect to both. You basically have to run multiple trials, look at them, and see how the system responds. So this would be our first order, and second order overall. And later on, we'll talk about that rate constant and how we're going to get that. All right, let's look at another example. Okay, in this example, we have this reaction, 2 NOs plus a chlorine making 2 NOCLs. And we have some data that's been produced. Okay, as in your chemistry travels, you might produce data like this as well, and you have to interpret it. So we have 4 experiments. In experiment number 1, we went from 0.25 to 0.5 and no change over here. Now this one went up twice. This went up double. But look what happened to the rate. It went up by a factor of 4, which is the square of the 2. And that indicates to me that it's a second order reaction with respect to NO. Now, I know your teacher is probably going to want you to prove it, and prove it with a calculation or a description or something. And I want to show you how to do that in this video so that we can practice it a little bit further on. So what you want to do in order to prove it is to realize that I'm going to move this up a little bit. The rate law for this reaction is going to be rate equals K times NO to the something, let's call it X, and Cl2 to the something else, we're going to call it Y. And I want to write this twice, one above the other, comparing the rates and concentrations from 2 different trials. So let's do that 2 over 1. So let's write it as rate 2 over rate 1 so that anybody reading your work knows exactly what you're doing, is equal to, let's actually put in the rates, 5.72 times 10 to the minus 6th over 1.43 times 10 to the minus 6th. Those are from the actual rates. Set it equal to a constant. I'm going to make a big line over here. And then I'm going to plug in the concentration of NO for trial 2, which is 0.5, and 0.25 for trial 1, raised to some X value. Don't know what that is yet. Well, I do know what that is. And the other side is 0.250, 0.250. And that's raised to the Y. And then what we want to do is simplify it just a little bit. Okay? This divided by this, we've been told, is already a 4. K over K. Now, I don't know what K is at this point, but I do know that whatever it is, it's a constant, so it's going to cancel. Let's get rid of that. And I don't know what Y is at this point, but I do know whatever it is, it's going to be a constant, and that raised to the Y on top and bottom is going to cancel as well. That leaves 0.5 over 0.25, which is 2, raised to the X, if we simplify that. So 4 equals 2 to the X. X must be a 2, and so it must be a second order reaction. So to keep this video short, let's take a moment, and I'll pause the video in just a second, and see if you can find out the order of reaction with respect to chlorine using 2 other experiments. You'll probably have to pick 2 different ones, and let's just give you a quick hint. I'm thinking that use experiments 1 and 3, because this stays constant while this changes. So take a moment, see if you can sketch it out, come up with a solution, and I will finish it in just a second. Pause the video. Okay, so if you found out that this is a first order with respect to chlorine, then congratulations. I'm going to do rate 3 over rate 1. I always like to keep the bigger rate on the top, just keeps the math easier. So 2.86 times 10 to the minus 6th, 1.43 times 10 to the minus 6th is equal to the constants, which are going to cancel. The 0.25, which now I know is raised to the second, but that's going to cancel anyway. Okay, I put that in. And then we have 0.50 over 0.250 raised to some y value. Again, I'm trying to prove that y value now. So this over this gives me a 2. That's going to cancel. That squared is going to cancel. And then I'm going to have this double is a 2 to the y, and therefore y equals 1. And so at that point, we would have a rate law that has been proven to be K times NO squared and Cl2 1. All right, so we have second order with NO, first order with respect to chlorine, and third order overall. All right, so if you were able to do that, congratulations. In our next video, I'll show a couple more of these, and as they get a little bit more detailed, sometimes there's 3 reactants and so on. So you can look for that video. In the meantime, happy solving and have a great day.